Okay, so we're going to do indefinite and definite integrals now. And so basically last time we talked about how if you have a larger amount of rectangles, the more amount of rectangles you have, the more accurate your area approximation is for area under the curve. Well, if you have an infinite number of rectangles, and this is the sum of all the rectangles in the curve, if you have an infinite number of them, then basically what you are finding is the definite integral. So an integral, if we think back to derivatives, an integral basically is an antiderivative. It does the opposite of what a derivative does. So if you think of derivative as kind of like subtraction, then you can kind of think of an integral as addition. It undoes what a derivative does. If you think about it in terms of, let's just talk about it in terms of velocity. So like if I graph velocity, and this is velocity, and it's meters per second, and then I find the area under the curve, and this is seconds, and this is meters per second. So what I'm actually doing right here when I find area under the curve is I'm taking meters per second and I'm multiplying it by the number of seconds, which gets me back to meters. So velocity goes back to distance. So an integral basically just undoes what a derivative does. A Riemann sum is the let's go back and we'll talk about a Riemann sum is the approximation of the area under the curve. And then there are four common types of Riemann sums that we talked about last time. It was left, right, midpoint, and trapezoid. So if we want to convert what this integral sign is back to a Riemann sum, this integral is going to equal the limit as n goes to infinity of the sum of all the rectangles starting at the first point to the last rectangle, because we want an infinite number of rectangles. So from rectangle 1 to rectangle infinity of, and then it's our function. Remember, area of a rectangle will be the height. So this is the height at whatever rectangle you're at. Times your delta x, which is your change in x, the width of your rectangle. And that's what this dx is for. This is the width of the rectangle. Now, when we're talking about integrals, the width of the rectangle is an infinitely small width. But we still have to write the dx there, because remember, we're not just integrating the function, we're integrating the function. We're finding the area under the curve, which is the function times the width of the base. All right? So the dx always needs to be there when you're writing integral. Okay, so let's, I'm going to do the first couple, and then you should try the next couple on your own. Maybe pause the video after number 2 and see if you get the same Riemann sums as I do. But for the first one, we're going to go limit as n goes to infinity of the sum starting at the first rectangle going to the last rectangle of the function times delta x. So that's what this one will equal. All right. Oh, I should go to n, not infinity. That should be n's. forgot my x-axis. Okay, so that's how you do that. Now let's talk about basically the derivative, going the opposite way of a derivative. Now, if I wanted to evaluate this integral, actually, let's talk about the derivative. If I wanted to take the derivative of x to the nth power, it's nx to the n minus 1, right? So you bring the exponent down, and then you subtract the exponent by 1. Well, if you want to integrate x to the nth power, don't forget the dx, because remember it's area that we're doing. Well, instead of subtracting the exponent by 1, we should add 1 to the exponent. And then before bringing it down, we add 1 to the exponent first and then divide by our new exponent. And then there's a plus c here. And there's a constant c here because think about when you take the derivative of x squared plus 2. If you take the derivative of x squared plus 2, then you just get 2x, right? Well, if I integrated 2x dx, I would get x, add 1 to the exponent, squared. There's this 2 out in front, divide by a new exponent. So I would get back to my x squared, but then I have no way of getting back to my plus 2, plus my constant. So that's what that plus c is there for, to tell me, hey, there may or may not be a constant here when I integrate. I might have to find it, so we have to add that plus c just in case. Anytime you integrate something that doesn't have boundaries, you're going to have to add a plus c to it. Okay, that's normal integration without bounds. So let's just do all of these without bounds. If I was going to integrate 2x plus 1, ignore 1 and 3 for now. We're going to just cross these numbers out. If I was going to integrate 2x plus 1, I would take my 2x, I would add 1 to the exponent, so there's a 1 right here if there's nothing there. So I'd add 1 and make it x squared. I'd divide by my new exponent, and then here's a plus 1, and a plus 1 becomes a plus 1x. So that's my integral of 2x plus 1. And then don't forget the plus c, because we have a constant there that we don't know about. All right, the integral of 3x squared minus 1, well, I would add 1 to the exponent first, so make it 3x cubed. I'd divide by my new exponent, which is 3. And then I would do minus 1x, and then a plus c. And then x plus 3 squared, well, I don't know how to do that yet, so let's just multiply it out. Let's make it x squared plus 6x plus 9. And so we integrate x squared and we make it x cubed over 3. Add 1 to the exponent, divide by our new exponent. 6x becomes plus 6x squared divided by 2. And the 9 becomes a plus 9x, and then plus c. And ignore sign for now. We'll do sign when we get to the trig unit. All right. These are called indefinite integrals when they don't have boundaries, but now we're going to work on definite integrals. If f takes on both positive and negative values, then the Riemann sum is the sum of the area of the rectangles that lie above the x-axis and then negative of the areas of the rectangles that lie below the x-axis. That's why when you're talking about integral, try not to say area. It gives us net area, not just area. So try not to say area anytime you're talking about integrals, because anything above the x-axis is going to be positive, but anything below the x-axis is going to be negative. So when you add up all the areas, it's going to be positive, negative, positive. So you're going to take away this section of it. And so that's what the integral is. If it just tells you area, then area is just always positive. So you don't want to refer to area and integral in the same way all the time. You can if everything is above the x-axis, but you can't for other situations. Okay, so these are two integrals, and we don't know how to do them by hand, but remember, integral means area under the curve. Well, 4 minus x squared is actually an equation that you should probably know. It's a circle with radius 2, but it's a half circle. It's only the top half. So we go out 2 each way, and there's our circle. And so if I want to find the integral from -2 to 2 of this function, well, this function is just the half circle. All I need to do is find the area of this half circle. Well, I know the area equation of that half circle is 1/2 pi r squared. So 1/2 times pi times 2 squared is 2 pi. So the integral of this is equal to 2 pi. All right, 3x minus 5 absolute value. Well, now remember when we were doing derivatives, we couldn't take the derivative of that. Well, for integrals, we can't take the integral of absolute value either. So all we'll have to do is we'll just have to know what shape that curve makes. Well, 3x minus 5 hits the x-axis at 5/3. And then we want to go from 0 to 3, so our shape looks like a V. At 0, my height is 5, if I plug 0 in here. And at 3, my height is 4. So, finding the area of the curve, all I would have to do is find the area of the two triangles right here. So it's 1/2 times 5/3 times 5 plus 1/2 times 4/3 times 4. Okay, so sometimes you'll have to draw a picture if you can't find the area on your own. So for this unit, we're going to just draw a picture for most of them, and then for the next lesson, that's where you'll integrate by fundamental theorem of calculus. Now, there are certain properties of the integral that you should know. When you integrate a to b of a constant, think of a constant as just a straight line. So if you integrate from a to b of some function c, all you need to do is find the area of that rectangle from A to B. So it's just C, the height, C times B minus A. And the integral, just like addition and subtraction of the derivative, it can be distributed across the two functions. If you have a constant, just like the derivative, you can pull the constant out of the function, evaluate the integral, and then multiply by the constant later. If you have the integral from A to C, so think about area. Let's say I have A, B, and make this C. A, C, and B. If I have the integral from A to C, that's from here to here. That, plus the integral from C to B, is that, should equal the area from A to B, right? All right, and here's comparison properties. If your function is above the x-axis on the interval A to B, then the area under then the integral will be above the x-axis, will be positive from A to B, right? And then if one function, if f of x is bigger than g of x for all A to B, then the integral from a to b of f of x will be bigger than the integral from a to b of g of x. And that makes sense too, because if your f of x is always higher than your g of x, then your area of f of x will always be higher than your area of g of x, will always be bigger than your area of g of x. And then I'm not really too sure what this one is. I think I wanted to add in two more. Don't forget here that there's another rule that I'd like you to remember. If the integral from a to b of f of x dx, if you want to flip the a and b, it equals negative the integral from b to a of f of x dx. Okay, so if you want to go backwards, then it's negative. And on a graph, if I was going back and I was doing this graph, and I was going backwards from 3 to 0, if I was finding the integral from 3 to 0 of absolute value 3x minus 5 dx, then if I'm going backwards, all this area above will be negative. So it's the opposite of what side it's on. If it's positive, it'll be negative. If it's negative, it's going to be positive. All right, so we're going to use properties of integrals to evaluate the integral from 0 to 1 of 4 plus 3x dx. We integrate 4 plus 3x by graphing it for now. Y-intercept of 4, slope of 3. And then we're going from 0 to 1. Well, to find that, we can just do area of a trapezoid. 1/2, because this is a straight line. 1/2 base is 1. Height 1 is 4 plus height 2 is 7. So it's 1/2 times 11 over 2. Okay? And if you know that the area from 0 to 12 is 18, so if we drew a graph of f of x from 0 to 12, and so we knew that this whole area was 18. And we know that the area from 0 to 9 is 10. And this whole area is 10. Find the integral from 9 to 12. Well, all I do is the integral from 0 to 12 of f of x dx minus the integral from 0 to 9 of f of x dx, and that should give me the integral from 9 to 12 of f of x dx. So 18 minus 10 is 8. Okay? Now, a lot of this is practice. So I put a lot of problems on your homework, but we're going to be doing that for classwork. So from now on, I would like you to take your homework out and just start working through the problems on this. The more you practice, the better you're going to get at it, and the more you'll understand it. Answers will be posted on Blackboard, so check there if you need to. Okay, see you later, guys.